Hello, my name is Andrew Joy, and welcome to my talk, GameFramework Extensions Technical Deep Dive. So I added the technical deep dive part to the talk title because I wanted to try and warn people ahead of time that this is a very programming heavy talk. There are a fair number of code examples on the slides to come. I would say don't worry too much about taking it all in, just try and get the general idea, because I provide all of the code at the end for you to go through at your own pace. I just want to kind of touch on the important things or the interesting things and keep it moving. If there are any non-technical people in the room, I do appreciate you coming, but I do apologize if you don't enjoy the next 40 minutes very much at all. So quickly, a little bit about me. I've been an Unreal Engine engineer for about 15 years now. I have mostly done contract projects, but recently I've been involved in a small indie game. It's an open world survival game. As the only programmer on an open world survival game, I have had to touch basically every system in the engine. So I'm pretty well spread. But also as the only programmer on an open world survival game, I have had to cut many corners in order to make sure that the game ever sees the light of day. So that's what I'm here to talk about now. 3 extensions that I've made to the Unreal Engine over the course of the past couple of years that have saved me a lot of time, usually by focusing on improving the stability and consistency and the flexibility of my code base. Again, I'll be providing all of this code at the end, so don't worry too much about taking notes and stuff. So the first one that I want to talk about is Pocket World. I should mention as well that with all of these, if they aren't directly applicable to your project, I'm still going to be jumping into some nitty-gritty little bits that will hopefully still be good takeaways, so you should definitely take at least something away from all of this. But yeah, Pocket World first. So give me a moment to get to what Pocket Worlds are. First, I need to make sure that everyone's on the same page about what a UWorld is. So quickly, just UWorlds are kind of the container for whatever game world we're in or the editor map that we're authoring. They basically run everything, so they run actor life cycles, spawning and destroying. They run the physics simulation, so tracing against the scene, and they run replication amongst basically everything else. They're super overburdened. And if you're playing a game, you usually just exist within a single game world. That's what you can interact with and what you can see. If you're in editor, you'll also have an editor game world. That's the map that you're currently authoring. And if you hit the play and editor button, you will keep that editor game world, but it will be duplicated into a game world for you to play. Once you're done playing and you hit stop, it will be torn down and you'll go back to your untouched editor world. So you generally have 2 worlds open at any one time when you're in editor. Sometimes there'll also be a loading world. That's for assets to be loaded into as you get ready to transition to it. And sometimes there'll be a lobby world. The lobby world is for multiplayer peers to connect to before they fully join the game. So the engine kind of runs all of these for you behind the scenes. You never know that they even really exist, and you don't really have much control over them at all. What if we could have control over them? What if we could create our own worlds and use them for whatever purpose we want, just kind of behind the scenes? What if we could create a scene capture world where we can render something for, say, a security camera feed without having it affect the game world or side effects from the game world like lighting affect our scene capture? Or what if we could create a mini-game world for us to play in like a little computer screen in the game or transition into temporarily? That's the idea of Pocket Worlds, basically giving us full control over UWorlds, letting us create and fully manage them and exploit all of their power for ourselves. So I'll give you a little example from my own game. This is a slaughtermelon. They're basically angry watermelons that attack you if you get near them. So this is it on the left as it appears in the game, a slaughtermelon landmark. They jiggle around with a skeletal mesh, and when you get close, they slam down and fire out spikes in all directions, trying to impale you. We have also attached a bundle of TNT to this one because we're going to try and blow it up. But before we do that, we have scanned it with our scanner. That's how it appears on the right-hand side. That's a 2D render of the same slaughtermelon, saved by the scanner into our codex that we can go back and look at another time. It has, as you can see, also recorded the TNT, which is a completely different actor that's attached to it, and that's all done for us in our scene capture background Pocket World. This is how the Pocket World appears in editor. So you can see Perdition, that's our editor world. Perdition server is just the game world, and Icon is our background Pocket World named Icon. The contents of the Pocket World is pretty simple because we just want transparent icon rendering. It just has basic lighting and post-processing. But if you want something more complex, you can do whatever you want. It's just a normal authored map. You can have full geometry in there or moving parts, whatever you want. This is how you create it. So I'm going to step through in a moment the 3 main steps to creating a Pocket World. But before I do that, I need to give you a quick overview of how this works. So you start by passing in an asset reference to a map that you have authored ahead of time. This is going to be used as a template that will then be copied and duplicated as many times as you want for as many copies of this pocket world as you want. And then you need to pass in some initialization values. This world initialization struct is an engine struct, so it's not blueprint accessible, and it contains a whole bunch of feature toggles, basically. If you want to turn off physics or AI or navigation, you can, if you want to reduce the overhead of your pocket world. This specific example is derived from a function in engine getPyWorld by loading from package. There are about 5 other places in the engine where worlds are created and managed. For example, there's getPyWorld by duplication, which is what I mentioned earlier for play in editor. So if this doesn't specifically suit you, you can go and find one of those other examples, and I'm sure that will better match your needs. So our first step here is to load the world into a duplicate package. What I mean by that is we aren't using the Unreal Engine loading system, because that's going to give us basically a singleton version of the map, but also it's going to have full control, which we don't want. We want full control. So we're going to manually load it using package loading. So this is how we're going to do it. We're going to create an inner and an outer package. The inner package is just a reference to our map asset, and that's going to be loaded for us. The outer package is just a unique empty package that we can use to contain it, and then basically treat it as our own. So this will let us have multiple copies of it. This will let us have full control over its life cycle. To create the outer package, we just simply create an empty package and mark it transient. The idea here is that this is fire and forget. We don't need to hold on to this. When the map is eventually garbage collected, this package will also be garbage collected. So we just want it here to contain our loaded map asset. Next, we need to load the actual map. We just use load package, and that'll load the asset directly from disk. But before and after that, we need to manually set on this world type preload map what kind of world we want it to be. So this is pretty important. There's a lot of different world types, usually game or editor, depending on what kind of world you want. But we're specifically going to mark it as a game preview map, because that will let us query it later on to determine if we are inside of a pocket world. That's very handy for feature gating if we want certain things to happen or not happen inside of a pocket world. And yeah, we have to mark it as game preview. Next, we use a helper function on UWorld, find world in package, to actually find the reference to our world in our loaded assets. And then, if that fails, we follow its redirector. If that fails as well, something has gone terribly wrong and we should just abort out, but this basically always works. The next step is to initialize it for play. This one's a bit simpler, so I apologize if your eyes glazed over on that last one. We currently have a loaded map, but it's not set up at all for play. So we begin by passing in our world initialization values struct here. This will do 95% of the work. That will again set up what features we want. For our purposes as a scene capture, we turn off things like physics simulation and pathfinding because they're unnecessary. If you want to treat this as a game world, so if you want to create your own minigame, this is where you would set a game instance and a game mode, but for scene captures, we skip that step. And then you initialize the world. Once you run through these 3 lines, the world is fully ready for play and you have full control over it, except for skylighting. So skylighting is unfortunately hard-coded into the engine to only process for whichever game world is currently the active world. So you do need to manually update it. In our case, it's as simple as doing it once because our lighting doesn't change, but if you have a full game world, time of day, etc., you will need to do it much more regularly. Finally, now that we have a world that's ready for play, we need to register it with the engine and then return it, and we're good to go. To do that, we create a world context. This is basically just telling the engine that the world exists and giving it a whole bunch of extra properties in case it needs to do certain tasks with it, usually in need of a game instance. We cheat a little bit here and we tell it that it's an editor world type instead of a game preview world type, because it doesn't affect how the world functions, but this will list it in that drop-down list of worlds that you saw earlier as the icon world in that list. We then set the game instance if we created one, if we set one earlier, and then we have to ensure that it gets cleaned up, because world contexts are completely separate. We need to make sure that they do get cleaned up eventually, but we also don't want the user of this function to have to worry about it. So we just assign this delegate to on-world cleanup, we check, and then we do the cleanup if necessary. Finally, we return the world. I should mention as well that UWorlds are not really designed to get garbage collected at all. They tend to have a lot of circular references that prevent it, but they also just aren't designed to clean up properly with garbage collection. You do have to manually call destroy world on these things. There are other ways that you can get around having to do that, like with a shared pointer, but Yeah, generally just remember to always call destroy world on these things. So that's how we get the pocket world. That doesn't give us the scene capture, so quickly to set it up as a scene capture, we can just create our pocket world simply with one line. We can then spawn just an empty actor in it like we would in any world. Again, you can use these just like you would the normal world that you play in. And then you can just add a scene capture component. Of course, if you want like the perfect camera angle, you can manually place that ahead of time, but this is just flexibility for us. It lets us use any world as a scene capture. Next, the initialization values are not blueprint accessible, like I mentioned, so we do have to manually wrap them in a blueprint callable function. I should mention as well that we default all of our pocket worlds to be not transactional, which means no undo history, because we aren't ever directly authoring them. They have been pre-authored, and we are loading them in into the background. So we don't want an undo history. We then pipe through some of the more important settings. I would say that there are many more settings on this struct that you can set if you really want fine-grained control, but these are the most important ones like physics. And then we just set a default game mode, something that's not intrusive in case we don't actually want to play anything inside of this world. Finally, we can test to see whether or not we are inside of a pocket world, just by checking if it's a preview world, like I mentioned earlier. This lets us do feature gating to turn certain things on and off inside of a pocket world. And that's pocket worlds. Like I said, that was a fair bit of code. If that was putting you to sleep, then get ready for the next one. So pocket worlds are very important to us. It saves us a heck of a lot of time. Not only do we use it for the scanner, we also use it to render out all of our item icons. So we do away with having to do art for any of those. We can manually set up the scenes to make them look real pretty ahead of time. And yeah, it's just been generally very, very useful. I would wonder, I guess, what other people might use it for in this room. So maybe if you have an idea, come and tell me later. It would be cool to know, because they are very flexible. Next, I'm going to talk about AAnyMeshActor. So this is completely separate from the Pocket World system, but we do use it extensively in the scene capturing system. I'll explain why in just a moment, but first let me quickly explain what an AAnyMeshActor is. So in the engine we have a static mesh actor, or rather a static mesh component. We have a skeletal mesh actor, or rather a skeletal mesh component. We don't have an AAnyMeshActor, and what I mean by that is if we want to set up an actor to use a skeletal mesh, we have to manually create that component, and we can't use a static mesh with it until we manually create that component as well. They're two completely separate code paths, and it's very difficult to unify them. So that's what an AAnyMeshActor is. We would be able to tell it, use this mesh, and it would just do it for us. Why would we want that? Well, there's two examples back in this slaughtermelon screenshot. So on the left, we have the landmark as spawned in the world. That is a landmark. Landmarks are just anything in our world that can spawn procedurally. So trees, boulders, gatherable sticks and twigs, explosive mushrooms, and things like the slaughtermelon. Most of those are static meshes, but there are niche cases where they would want to be skeletal meshes. So we don't want to end up having a static landmark and a skeletal landmark or anything like that. We want to design our landmark classes feature first. We want to have gatherable landmark and compound landmark, that it consists of multiple smaller landmarks, that kind of thing. By using an AAnyMeshActor as the base, we get to avoid doing that entirely, but we still get full mesh access in all of the parent classes all the way up the tree. And yeah, makes it very powerful for things like our landmarks. It's also used in the scene capture system because the same logic that we apply to use any mesh on this actor can be transferred and used to also copy all of the mesh components on the actor and duplicate its appearance without needing to spawn any of its side effects. Spawning a slaughtermelon inside of our pocket world for scene capture purposes would be catastrophic because, well, in general, a lot of these actors can have events in begin play, like they register to lists, or certain things in destroy that they have happen, side effects that we don't want to have happen. If we were to copy this TNT in, when we destroy it, it would explode and spawn a particle effect in its wake, which would then persist through multiple renders in the reused scene capture world. By using an AAnyMeshActor and just copying the appearance only from this other world, we get to do away with any risk of side effects, and we just have a very stable scene capture system. So how does it work? Well, we aren't going to do the old Game Jam classic of using both a static mesh and a skeletal mesh. We're going to do something a little bit more professional, and we're just going to use a mesh component. So mesh component is the base class of static mesh component and skeletal mesh component. I'm sure a bunch of people can already see where we're going with this, but the general idea is we're going to be hot swapping what mesh component we're using under the hood, and then exposing it as the base class of mesh component. So if you were to tell this actor, it's already using a static mesh. If you were to tell the actor to use a skeletal mesh, it would create a skeletal mesh component, copy across any configuration you did to that old static mesh component to maintain state and make it as transparent as possible, and then destroy and tear down the previous static mesh component. The idea is to do that so automatically and so cleanly that you never know that it's happening, and yeah, it's just kind of magic. This is a stripped down version of the AAnyMesh header file. You can see here that we're storing and exposing it as a simple mesh component. We also allow you to set and get the mesh asset as what is unfortunately called a streamable render asset. So note that this is different from the component. This is the actual asset that the component will use to render. I really wish that this was called UMesh or UMesh but to be fair, the engineers did not expect this weird use case. So it's a streamable render asset. We then have the option to pass in an override class in case we want fine-grained control over what component we're going to be using. All good? Fine-grained control over what component we're going to be using instead of letting it be inferred from the mesh asset that we're passing it. And down here as well is the copy mesh function. I'll get back to both of those in a moment, but let me quickly show you how it works in action. This is the slaughtermelon. You're going to have to forgive me the use of constructor helpers. It was a necessary evil for demonstrative purposes only. We are going to be setting a skeletal mesh on this slaughtermelon, and when that happens, it will do what I said earlier. It will create a skeletal mesh component, copy across properties, and tear down the old static mesh. From there, we can modify the mesh component just as a base mesh component, which has most of the useful properties already, such as receiving decals. And if we really want control over the skeletal mesh component, we can still access it with a templated override of getMesh. Let me quickly show you another example. This is a fence building. It's basically a spline fence that you can place in the world and link them up. We don't want to give it a mesh asset yet, but we do want to tell it that it will eventually be a spline mesh component. So we do that with the override class, and you see down in the bottom there that it now has a spline mesh component ready in Blueprint to set whatever mesh we actually want to use. We can still modify it here as a generic mesh component. We can set mobility and collision profile, all of the really important stuff. Or we can directly access it as a spline mesh component if we want. So yeah, pretty powerful. Let's actually talk about how it actually works. I've broken it down into 6 steps, and I promise I won't go through them all. Some of them are incredibly boring. For example, number 1, sanitize override class. We're going to skip this one, but the gist is it just makes sure that the mesh asset you're passing in is compatible with the override class. Whatever. We're going to go to number 2 and create the component. When creating the component, we first want to make sure we aren't doing unnecessary work, so we check if we even have to create the component. If we don't, we just apply the new mesh and then early out. If we do create the component, first we need to see if we are inside of a constructor, if set meshes have been called from inside of a constructor, which is actually most of the time. This is an easy way to do it. It's used extensively throughout the engine, so maybe that's one takeaway if you don't like AAnyMeshActors. If we are inside of a constructor, we create a default sub-object of our component like you normally would for any C++ class creating a component. Or if we aren't inside of a constructor, we just create a new object that we will then attach and register manually later. The next step is to copy over its properties. So this one gets a little bit daunting. We are going to iterate over all of the properties on our mesh component. So note that we aren't iterating over all of our static mesh properties or our skeletal mesh properties, only the mesh component base class, because properties on static mesh obviously don't exist on skeletal mesh and vice versa. We can't persist those settings, but generally they're fine to be lost anyway. You won't be changing from static, skeletal, whatever. So yeah, we iterate over all of our mesh component properties, and for each mesh component property and parent properties, we will retrieve the default value from the class default object, the CDO of that old mesh component, what it should be set to by default, and we will retrieve what it's currently set to. We then compare the two properties, and if it has changed, we apply that change to the new component. So this might look a little bit complicated, but the idea is we're just iterating over properties. We are comparing to see if we have made a change, and if we have made a change, we apply it and we propagate it to the newly made component. The next step is to gather and then reattach children, because this mesh that we're swapping out might have, say, a child mesh component that's a sword held in a character's hand, or like a particle effect, like a Super Saiyan effect on the character, or something like that. We want to make sure that we persist any attached children, and since we're eventually going to destroy this old component, we have to gather and reattach them first. So the gather step is a bit interesting. we need to, first of all, call this getChildrenComponents function. That's an easy way, but that only works if the actor has been constructed. If it hasn't been constructed, we need to manually find all of our attached components inside of the constructor, inside of this pool of just loose objects. So we call for each object with outer, and that will iterate over all of our inner objects on this whole actor. We're looking for just loose objects that will eventually be attached to our old mesh component when the construction step has been fully run. That's what we do here. We gather those components, and then we're good to go ahead with reattaching them. I won't go through the reattachment step. It's pretty straightforward. We just reattach it to the new component. Same thing for destroying the old component. We just tear it down and move on. So that's set mesh. Relatively straightforward, just a couple of complicated bits. I mentioned that we reuse a lot of that logic for copy mesh. But how do we do that? Well, the slaughter melon's back. So let's use this as an example. We have 3 mesh components on the slaughter melon. Rootmost, we have a skeletal mesh component for the slaughter melon itself. That is the green and red jiggly bit. We also have a spikes static mesh component. That's for the white spikes at the base. When we fire them out, we just hide that component and spawn projectiles at each of those sockets and fire those out instead. And when the slaughter melon rearms, we re-enable that component, right? We're just faking that we fired out those spines. We also have the TNT component. This component technically belongs to a different actor, but it still exists within our attachment hierarchy, just because that's how the component attachment hierarchies work. So, in order to copy this, we're going to apply our set mesh logic recursively. There's going to be a little bit of recursion coming up, I warn people. So we step in and find our rootmost skeletal mesh component. We create a copy of it, and we copy over the component properties like you already saw in set mesh. I would point out one difference here is that we also copy over static and skeletal mesh components, because in this case they do actually match. So we copy over everything. We want an exact copy. Next, we gather children, and if we were continuing down the normal logic path, we would reattach them and then destroy the old component. But that is, needless to say, very destructive for the actual actor that we're copying from. So instead, we will gather children, and then we will step back into copy mesh recursively. So for each of these child components, we will create a new copy properties, gather their children, step back in recursively until we have shallow copied the entire component hierarchy. That way we can get, an exact visual replica of what we are trying to copy. They're the exact same steps, except for that one change I mentioned to number 2, and a kind of important change to number 3. This one gets a little complicated. I apologize. This slide will hopefully illustrate the issue. This is taken from our game. We have the build tool out, and we're trying to build a shed here next to our gene house. We have a holographic representation of what we're trying to build, and we can move it, rotate it, etc., see if it fits and overlaps anything. We don't want to spawn the actual shed that we're attempting to place here, because that has side effects like flattening the ground and removing grass. We just want to spawn a representation of it. So we use an AAnyMeshActor, and we copy the appearance of this shed. Unfortunately, the niche case here is that the shed, we have to copy the class default object of the shed. The problem with this is that the shed is a blueprint. That's a bit of a niche issue, because blueprints don't actually have their components just floating around ready to go, any components that were added in blueprint. We have to manually parse the construction script of a blueprint in order to gather their children properly and then copy them across to the new actor. So that's what we're going to do here. We're going to manually parse a blueprint construction script. We step in, see if we're copying from a blueprint, and if we are, we're going to gather all of our parent blueprint classes, because we could be 3 or 4 deep at this point. Then, for each blueprint, we're going to recursively step into our ConstructionScript nodes, step all the way down these trees, and find which nodes are going to eventually create a component, and then gather that component. That's what the search node function does. It's a recursive lambda, as you can see here. We step in for each node, again, all the way down the tree. We find the ones that will create a component. We gather that component, and then we do a little bit of a hack here. So we need to set up attachment for this recursively found component. Unfortunately, this is a little bit destructive, because this will modify the actual properties on the blueprint class default object, but it also doesn't have any meaningful side effect, and it saves a lot of work, so we'll do it here instead. We just manually set up the attachment, then we continue to recursively step down this ConstructionScript tree, finding more nodes, setting up more attachment, and then we're done. This probably overkill extension allows us to copy blueprint CDOs that have added blueprint components, and that's it just works. So that's AAnyMeshActor. I would say that the quality of life from using this has been profound. It's been good. Basically, we don't have to worry now about using a specific kind of mesh. We can design our base classes to have any mesh they want at any level in the base classes, and still just kind of use whatever at the endpoint, like the slaughter melon endpoints. It has also given us the power to just basically copy the appearance of actors, which is incredibly useful for a lot of purposes, more than just those blueprint representations. And yeah, it doesn't have any dependencies, so it can just drop into any of your projects pretty easy. Last, I want to talk about RepHelpers, but I need a little bit of backstory here. So last year, I was here talking about replication. I did a talk called Replication Without Compromise, and I talked about adding replication support to a couple of unreplicated types in the engine, specifically UObject, tmap, and user widget. It wouldn't feel right if I kind of came again and didn't touch on replication because I love the topic. And we happen to recently have done a full upgrade to use Iris. Iris, for anyone not aware, is basically the next generation Unreal Engine replication system. It's been dog-fooded in Fortnite, and it's slowly being integrated fully into the engine. It's very powerful, and I would suggest upgrading. But as we were doing this upgrade, we decided to also upgrade the rest of our replication system. So we implemented some Iris-adjacent replication features. We added push model replication and actor net dormancy. Both of those are tied a little bit to Iris, but push model in particular is very much preferred by Iris. So if you do upgrade to Iris, or if you're already using Iris, you should definitely also be using push model. You can not, obviously, but it works much better with push model. And yeah, that's what I'm going to talk about now. While we were doing this upgrade, because it was a huge upgrade, we wrote this RepHelpers header file with a whole bunch of macros and functions that made the process a lot easier for us. And we still use them today. They've greatly improved the stability of our replication code. And yeah, I want to share a couple of them now. Before I talk about what push model and net dormancy are, I want to quickly talk about how the replication system works. And it works by polling. So every replication frame, we run into a net tick, which will iterate over every single replicated actor in the whole world. So if you have 10 of them, 100 of them, 1,000 of them, it'll iterate over every single one and prioritize them. It'll then iterate all of their replicated properties, doing comparisons along the way with the stored shadow state, the previously replicated state, and then if there has been a change, it will push that change out to clients. That can get pretty intense. As a normal game, like with maybe 10 replicated actors, it's a very good system, it's very powerful and very easy, and it's very hard to stuff up using. But as soon as you get to 100 actors, or in our case, many thousands of replicated actors, it basically destroys your server. If you're playing as a listen server, so a server host, then your computer will just brick up. If you're playing on a dedicated server, you'll probably burn the warehouse down. It's pretty extreme. So there are two optimizations that the Unreal Engine replication system offers to make it much more performant. The first is push model. Push model lets us manually mark specific properties as having been dirtied, so then when we iterate over the properties, we still iterate every actor, but when we iterate the properties, we only do the comparison for properties that we have told the engine have been dirtied. So in this case, we only check scan progress. That's a pretty good performance improvement, and it's pretty easy to implement. You do need to turn it on elsewhere, but that's easy enough to Google. This is basically just how you use it directly. This is an example straight from the actor CPP file in Engine. You just do this call to mark property dirty from name, and it just marks it dirty for you. You need to do that every time you edit the property, in case it has already been replicated. Net dormancy basically takes this a step further. Net dormancy lets you tell whole actors to go to sleep across the network. They will still exist on clients, they just won't send any replication updates, and they won't even be checked for replication updates. Furthermore, they will tear down their entire replication state on the server, letting you reclaim all of that memory and just generally cleaning things up. So in this case, we have told the slaughter melon and the crop to go net dormant, told them to go to sleep. We've reclaimed that memory, and yeah, we're still using push model because they're kind of a complementary system. One is for actors, one is for properties. And in this case, let's say we have 1,000 actors that are replicated. If we tell 900 of them to go to sleep, not only have we saved a lot of processing, but we have saved a lot of memory as well. I should point out before I go any further and explain what net dormancy is, there is an iris setting here, push model, skip undirtied replication. I think it even works outside of Iris, but it got added with Iris. Basically lets you treat push model replication similar to net dormancy in that it will skip ticking entire actors that haven't had a dirtied property. It's not a silver bullet though. It doesn't tear down their replication state, so you don't reclaim memory. You only get that performance improvement, not the memory gain. So net dormancy, I mentioned you can tell actors to go to sleep and then to manually wake up. When they wake up, they recreate their state, by the way. It's actually easier just to tell them to always go to sleep, unless it's an actor that will be replicating a lot. This is how you do that. They will then spawn and then immediately try and go to sleep until woken. You just set it to dormant all. When you want them to wake up, you do this call to flush net dormancy, and that will wake them up temporarily. It'll let them send a few updates, and then as soon as they stop updating, they will then go back to sleep and tear themselves back down. It's important to do this before you modify any replicated properties on the actor, because it's recreating its state, right? If you modify the property, then recreate the state from that actor, it might not detect that property has changed. In practice, it actually usually just works anyway. It's a pretty smart system. But there are some edge cases where it doesn't, like with fast arrays. So generally, it's better to always be in the habit of always doing this call anyway, before you modify the properties. So this is both of them side by side. They're pretty similar, and they both achieve a pretty similar goal. Let's see if we can take them a step further, and I'll show you what we eventually got up to in RepHelpers.h. So let's take them a step further. What happens if we move flush net dormancy into our set hidden property accessor? Well, now we don't run the risk of never calling it, or run the risk of calling it in the wrong order. We always call it before the property was modified. Let's take it a step further again, and only do all of this if we actually want to change the property. If we set it to true 10 times in a row, we don't want to flush it 10 times and mark the property dirty 10 times. So we just gate it, we guard it like this. And then also, let's take it a step further again and add a call to our onRep, our repNotify function. So repNotifies are U functions that can be associated with a replicated property to be invoked on the client when an update is received to that property. That lets you react cosmetically on the client to certain property updates. Usually you also want to manually call these on the server where you modify the property, because the server is usually also a listen server, so it's also playing the game. You want it to react cosmetically, and yeah, you want to manually invoke it. That does happen for you in Blueprint. If you modify a replicated property in Blueprint, it will also invoke the repNotify function associated with it, but it doesn't happen in C++ because it's C++. So you need to manually call it. Adding it here basically brings us closer to parity with Blueprint and makes it much more consistent. What if next we want to modify 3 of these properties? We would need to copy all of these changes into their property accessors, even if they had them, and yeah, we'd end up with a lot of duplicate code. Instead, we're just going to boil it down to a simple macro that does exactly what we just did, but with a few extra bells and whistles. The main thing here is it will automatically detect what kind of repNotify function needs to be called, whether or not it's 0 parameters, 1 parameter, 2 parameters, if they even exist, and invoke it for you. So it's all very kind of automatic and under the hood. You just use this wherever you would want to modify a replicated property, and it even makes it very easy later on to find where you're modifying replicated properties, because you just search for rep sets. Anyway, this is the implementation of repSet. It's very similar to what you just saw, except one small difference. We have to evaluate our new value first. For this exact case, we don't want to accidentally spawn multiple explosions. Because it's a macro, it will repeat that line multiple times. We just evaluate it once and then use that evaluation multiple times. So yeah, we do our guard, we do a call to rep dirty that will do both our dormancy flush and our property dirty. We then apply the value using some beautiful decal type magic, and then we do our notify. And again, this will just automatically infer what needs to be called, if anything needs to be called, and with how many parameters. This is the implementation of rep dirty. It's pretty straightforward. If you don't care about these rep helpers, there are still some cool takeaways here. So this is how you get the push ID of any actor using the push model system. This is important in a moment. But the more important thing is this cool little feature thanks to the Unreal Header tool. When you compile a replicated class, it usually lists all of the replicated properties for quick, easy access in an array on the class itself. That's accessed by its rep index, so it's indexed in that array. When you compile this class, it will also create a static enum in the header file called enetFieldsPrivate that also associates property names with these rep IDs. By using a little bit of macro magic here with property name there, we can just directly access it at compile time and save a heck of a lot of work. And yeah, then we have our rep index. That will be important again in a moment. So next we flush our net dormancy, like I said, and then we just mark the property dirty. This is just an expansion on what the mark property dirty from name macro already did, just for simplicity. And yeah, then we have our rep dirty macro. I would say even if you don't take the rest of rep helpers, this macro itself is still an improvement in my opinion over the push model macro, because not only does it also work with dormancy, which you'll probably also be using, but it just has a lot less parameters, it infers a lot more, so it's a lot safer to use. You can't accidentally stuff up what you're passing in. This is the implementation of rep notify. I'll try and get through this one pretty quick. I don't want to bore people too much more. But the gist is we only try to invoke a notify function outside of the constructor. We don't want to do it while there is no replication state. Then we need to find what function we want to invoke if it's even associated with a replicated property. This is again done directly with this enet fields private and a bit of macro magic. We just access it in our class reps, see what rep notify function is associated with a replicated property, and then retrieve it. Once we've retrieved it, we then use that name to get the actual function pointer, and then we do a check. Because I mentioned earlier that rep notifies can have either 0, 1, or 2 parameters. 0 basically just means invoke me and something has changed. 1 parameter gets past the previous state of the replicated properties, then you do comparisons, and you might want to do a different effect based on what's changed. 2 parameters is super rare, but it is actually a thing. It lets you also take a parameter that details how it was replicated, basically a bit of replication metadata. I haven't actually ever seen it used anywhere, but it is a thing, and it is kind of nifty to have, but we just don't support it because it's kind of very difficult to get in this macro, and it's got a very niche use case. Anyway, we then invoke the macro, we then invoke the rep notify with either 0 or 1 parameter with another little bit of magic, and then we're done. That's our rep notify function, just dynamically invokes any rep notifies associated with the property. This is the header file. Rep notify and rep dirty are the workhorses, they do most of the work, but there is the family of setters, mostly container accessors like add, insert, remove, empty. We also have rep class, rep property, rep properties. That's basically a drop-in replacement for get lifetime props. I won't go into that too much, I'm basically out of time. But yeah, that's just a quality of life improvement. Lastly, I want to very quickly mention replicate immediately. So replicate immediately does what it says on the tin. It forces an immediate replication of any one actor. This is quite important for ensuring that final state of an actor gets properly replicated over to each client. If you were to destroy an actor, it just usually sends just the destroy signal and not what its final state was. And yeah, we sometimes want that final state on the client. This is how you use it in the destroyed function. There is an alternative function called forceNetUpdate already implemented on actors. But what that does is it says, next replication tick, force me to replicate. And by then the actor's been destroyed. Why might you want this? Well, there's a very good example in Pawn itself. This is actually what inspired it. In Pawn, there's a replicated property called controller. And if you set that, on the server you get a possess or an unpossess event, and you can react accordingly. On the client, it gets replicated through, and then a rep notify function will also call possess or unpossess on the client, and you can use the same code path on both server and client to react to these changes. However, if you destroy a possessed pawn on the server will get possess and unpossess, and the client will get nothing, because the client purely gets the destroy message and not the final state of the actor. You could manually work around that, but just generally there's a lot of other use cases where you would want to be able to react to the exact final state of the actor on the client, so that's where replicate immediately comes in. Like a quick example is just with gatherable landmarks for us. We want to sometimes play sound effects if they were fully gathered, but not if they were destroyed by TNT, for example. So, you know, we just force a replication of how many gathers were remaining, so we know on the client if it was destroyed naturally. Lastly, I will quickly mention this explosion actor. So when we spawn this, it creates a big particle effect, and it deals damage to other actors in the vicinity. It fires off some explosion events, and then it destroys itself immediately. Because it existed for such a short period of time, it never gets replicated to the client, and the client never sees the explosion. They only get the damage events, the side effects, and they're left wondering what happened. By putting replicate immediately in either begin play or destroyed, you will guarantee that it exists on the client for at least a single frame, And yeah, you'll guarantee that they always see the explosions. This is the implementation, last slide I swear. This is the implementation. We're going to iterate over all of our client connections, and that makes it safe to call on clients because it'll just do nothing. For each client connection, we retrieve our actor channel. These are basically the data channels that we push actor updates through to clients. So yeah, we retrieve the actor channel, and then we force the replication to happen down the bottom there. If the actor channel doesn't exist, but we can create it, so this is the case for the explosion actor that I just showed you, we then go ahead and manually create the actor channel and start replicating through it. We force the replication to happen. I should point out this is exactly what happens if you were to call an RPC on the explosion actor in begin play. It manually creates the channel for you, but then it also sends the RPC. So we want to avoid that unnecessary step and just boil it all down to a single easy function. And yeah, you just call replicate immediately and it fixes the problem. So that was RepHelpers. That was a whole bunch of little things. I hope some of those can be helpful. They've definitely helped us a lot with consistency. And yeah, that's the end of RepHelpers and the end of my talk. I hope you guys managed to take something out of it. Thank you for listening.